Next up, we'll look at hypothesis testing for two sample means. So they'll give you two samples this time, two groups, and we'll look at averages. For our hypotheses, this should be very similar to a two proportion test, where we're going to start with assuming that the averages are equal, meaning if we subtract them, it should be equal to 0. Alternatively, we'll try to show that the difference is greater than, less than, or not equal to 0. Formulas here for mean and standard deviation. So when I'm finding the mean, I am going to subtract the two averages, should be just equal to 0. Standard deviation, we'll have to use this little formula to calculate standard deviation. Remember, every time that we have these two sample means, things get a little tricky with degrees of freedom, so we will need to use our calculator here when it comes time to find the p-value. We'll do as much as we can without it, but then eventually we will need to run the test. So our example says, researchers investigating how the size of a bowl affects how much ice cream people tend to scoop when serving themselves. At an ice cream social, people were randomly given either a 17-ounce or a 34-ounce bowl, both large enough that they would not be able to fill to capacity. They were then invited to scoop as much ice cream as they liked. Did the bowl size change the selected portion size? The summaries are below, but they are actually not below, so we're going to go ahead and write those in ourselves. All right, go ahead and take a minute to write down these summaries. For the small bowl, they had an average of 5 ounces, standard deviation of 2, and 26 people had a small bowl. Large bowl had an average of 7 ounces, standard deviation of 3, and only 22 people had that large bowl. Now it does say to test an appropriate hypothesis, so I know that I'm going to be running phantoms here. So we'll go ahead and start with listing what's happening in the parameter. Okay, again, two groups, so I should probably have two mu values. So I'm going to have mu1 and mu2. Okay, mu1 I will have represent the average ice cream in small bowl. mu2 can be the average ice cream in the large. Hypotheses. I am going to start with assuming that the bowls are the same, so mu1 should be equal to mu2, meaning when I subtract them, mu1 minus mu2 should be equal to 0. Alternatively, let's see what we're trying to show here. It says, did the bowl size change the selected portion? So I'm not looking at is one greater than the other. I'm just looking for a change, which would be a not equal to. So this is going to be a two-sided test. Okay, next up I'm checking my assumptions. Same assumptions as always for means or for averages. So it should be random here. Looks like they were randomly given the bowls, so randomness is met. Looking for less than 10%. I definitely think that 26 and 22 bowls is less than 10% of all bowls. Okay, this next part, I'm checking for that nearly normal. It doesn't tell me anything about the distributions. It doesn't provide me any pictures, and my sample sizes are a little bit small. I want them to be 30 or greater. So I'm going to say I assume the distributions are normal. You might want to include here that you are possibly concerned with this shape and this last condition, but you're going to proceed anyway. Okay, the last condition is that my two samples must be independent, definitely independent here. Can't be eating out of the same bowl, two bowls at the same time. So definitely independent samples. Okay, N is where I am naming the test. This is called a two sample or two mean. Put mean there as well. T-test, using T now instead of Z. And T is where I will find the difference between my two means. Since I'm looking at sample means, I'm going to write that as x bar 1 minus x bar 2. So I'm going to take the average from the small bowl, which is 5, and subtract the average from the large bowl, which was 7. So I'm looking at -2. Okay, for O, I'm obtaining that p-value. I'm going to try to build a model, so I need an expected value of my sample means, so x bar 1 minus x bar 2. Again, this should always match that null hypothesis, so I'm going to assume that it is at 0. Standard deviation. And we're going to use this little formula up here. So I'm going to take the square root of my first standard deviation squared, so 2 squared, over the first sample, so 26, plus the second standard deviation squared, so 3 squared, over the second sample. Whoops. So roughly standard deviation of 0.75. Once I have my mean and standard deviation, I can draw my model. Mean is at 0, standard deviation of 0.75. I'm going to drop down my test statistic, which was over here at -2. A not equal to means that I should have shading on both the left and the right. Since this -2 is already to the left, I'm going to start with shading that left. Then I'm going to estimate and just make sure I have roughly the same shading on that right-hand side. Again, I will change this -2 into a t-score. And here's typically where I would use TCDF. If I try to go to that TCDF right now, it's going to ask me for degrees of freedom. I don't have those degrees of freedom, so instead I'm just going to run a 2-sample t-test on my calculator, and it should give me the p-value. So I'm going to stat test. I'm looking for a 2-sample t-test. I have stats. I'm going to go ahead and type those stats in. So for small, and then for large, changing my hypothesis here. And remember that pooled is always no for averages. So I can leave that as no. I'm going to go to calculate. Looks like I did well on my t-score, so then it gives me my p-value of 0.0115. Once I have p, I can make a conclusion. So since 0.0115 is less than 0.05, we reject H naught. Rejecting H naught means that we have evidence to suggest that the alternative is true. So looking at my alternative, looks like the average ice cream in a small bowl is different than the average ice cream in a large bowl. Okay, again, make sure you're good with running that test in your calculator. You cannot find this without that calculator, so make sure you're good with that part. There is technically one other type of test that we looked at. This is a paired sample. So paired samples typically are given to you in a table. So I'm just going to like squeeze an example in over here. So maybe I would have I don't know, like the original test and then the retake score. And I would look at people, so maybe this is person 1, they got a 50 on the test and then an 80 on the retake. Then person 2 got a 40 on the test and a 60 on the retake. Person 3 had a 50 on the test and a 52 on the retake. Okay, this is a great example of paired data because these columns here, this data is paired based upon the person. I cannot just take these two numbers and flip-flop them. If I take 80 and 60 and I switch, I've switched people's grades around. That can't happen. So this would be paired versus having just two independent samples. Your conditions are the same. You're checking for random, less than 10% and nearly normal, but then instead of checking for independent samples, you should be checking for paired data, but the differences should be independent. What's nice about this is you're going to treat this problem exactly like a one sample mean, confidence interval, or hypothesis test. The only thing is you should use the differences as your data. So you could type this stuff into your calculator. We usually just typed in then L3, calculated those differences. The process is then the exact same as we saw on this previous page with hypothesis testing for one sample mean. The only difference is you're focusing on those differences rather than one set of data.